All right, welcome back, students. We are now going to finish all the way up through number 64. And we just finished figuring out how to get a formula given the percent composition. So we'll be moving on to number 56. If you know the definition of stoichiometry, your prob's going to get this one right. Okay? And you better know the definition of stoichiometry. That's all I got to say about that one. You'll get it. All right, number 57 is going to involve a little bit of extra research, like stopping the video and grabbing my stoichiometry packet, which you never threw out as agreed on the front page. And if you go to number 6 on page 3, and I did have you staple the questions onto the back so you can see what the question was and how we solved that one. But this problem in the test is very similar to that one. If you have that example to follow step by step, again, this is one that I'm going to need to see your work to show me that you were putting some effort forth on a problem like this. Okay, 58 deals with actually calculating an equilibrium constant. Okay, so just remember the products go on top, the concentration of the products on the top, and the reactants go on the bottom. Coefficients become exponents, and then you plug in the numbers and solve. So we'll give you a hypothetical problem given two concentrations at equilibrium, and you're asked to calculate the equilibrium constant. So you're going to write your KEQ expression. The product, as you can see right there, has a coefficient, so you better raise that to the second power. And then on the reactant goes on the bottom, and it has no coefficient. And then since you're given the numbers, you're going to plug that in. A little bit of working with the exponents. You will have to do that on the test too, so make sure you can calculate that correctly. And when you punch in those numbers and solve, you should get 510. Of course, 2 sig figs, so your calculator is not going to say 510, but you will round it to 510 because of significant figures. And that's how you do an equilibrium constant. Another one, show your work. Another one that I think you can get, because we did this, and we did one like this on the group quiz as well. Okay. You can also, of course, write this as 5.1 times 10 to the second. So if they show you that form, realize that that's the same number. Okay, moving on to number 59. When we talk about equilibrium, we're talking about going back and forth constantly. It never stops. The pucks are going this way, the pucks are going that way. And when they reach equilibrium, those pucks going left, pucks going right, bam, all over the place. What is equal in a system like this is what you guys already have written in there. There's your equilibrium reaction. What is really equal is the forward rate and the reversed rate of the reaction. The pucks going this way, the pucks going that way are at the same rate. And that's when you achieve equilibrium. All right, so here, stop and write this all down and come back when you're done. So hit that pause now. All right, welcome back. You got this diagram all drawn, and you can see this diagram is different than the one that was on the first part of the test. You end up uphill, and the delta H is positive. I don't know if you wrote that part that was on the top, but definitely do that now. The delta H positive means it's going uphill. That's endothermic. If something is endothermic, if there was an endothermic reaction in here, it would feel cold to the touch. It's like those little bags you can break for ice packs in the first aid kits. You break them, you react the chemicals, and it feels cold to the touch because it's absorbing energy from around it. It's like it's uphill. Where did that energy go? It sucked it out of the environment around it, and that's why it feels cold to the touch. Okay, so that is number 60 about an endothermic reaction. Now 61, the difference between sulfur and sulfide is the fact that one is an ion and one is not. Sulfur, no charge. Sulfide, -2 charge. They're very, very different in how they react, their properties, way different, these two species. And they're also different in size. This is the size in nanometers of a sulfur atom, and this is the size in nanometers of a sulfide because it has picked up 2 electrons, and electrons are what make the size of an atom. So if you have 2 more minuses and no plus to pull them in, you just added 2 electrons, it gets bigger. So those negative ions are bigger, and that is on this periodic table. There's a nice little drawing of that concept. This was the two-sided periodic table. That's one of your reference sheets. You might as well dig this one out because I'm going to make reference to it in just a minute here. Okay, which is right now. Okay, I didn't know it was the next slide. All right, so this side, which is sort of the periodic table broken into groups and areas, tells you that that family or column, also called a group, family or group, group 1 is the alkali metals, and you can just follow along on this sheet and emphasize and just make a note to yourself that this is the reference that you're going to need. That's the alkaline earth metals, and then we drop over to group 16 using the IUPAC numbering system, which gives us the chalcogens and, of course, the halogens, very common group, and the noble gases. They used to be called the inert gases. And all that stuff is there for you on this reference sheet, which is awesome. Okay, so another one that you can get. We're getting a good review and getting through some good stuff here. First of all, for number 63, for purposes in a chemistry class, atomic weight and atomic mass are interchangeable. Okay, and you can pretty much call them the same thing. The question for this one is, why, if the whole system is based on carbon 12 weighing 12, why does carbon have an atomic weight of 12.011 grams? Of course, the answer to that is some of those atoms have extra neutrons. It's rare, but there are some carbon-14, and that raises that average up a little bit. Those are called isotopes, and having those isotopes with a couple extra neutrons kind of tweaks that average up. Yeah, 99% of it carbon-12, but there's a small percentage that weighs more, and some carbon-13 thrown in there every once in a while. So that causes that average to go up a little bit higher. And that's kind of what that question is getting at. All right. So for number 64, you can just look back at the earlier part of your notes to number 24, where we did the 1s2, 2s2, 2p6, and so on. And you just keep chanting. You go right through. So you can use your electron configuration periodic table for this one. You can write out this electron configuration, but that should give you a good idea for number 64, which is actually now our 16th question. So that is going to be that for part 4 of the test. Good luck. Let's make this one our high score and then wipe out another lower score. Remember how important that is. Let me just check. Yeah. Okay. The next one. We'll get to that one next time. Okay. So study hard. Make this a good time. Come in organized and ready to roll. End of video 2 for part 4. Good luck. Bye.